Welcome to Visual Algebra Lecture 2.6, Symmetric and Alternating Groups. In the previous lecture, watch that one first if you haven't already. We learned all about permutations, various notations, and how every finite group is isomorphic to a collection of permutations, which is called Cayley's theorem. In this lecture, we will study two very important groups of permutations. The set of all permutations of a finite set, called the symmetric group, and the set of all so-called even permutations, called the alternating group. Remarkably, these have a number of Cayley graphs that can be built on the skeletons of Platonic and Archimedean solids, so be prepared for a bunch of beautiful, colorful pictures throughout this video. In the beginning of last lecture, I defined the symmetric group Sn to be the group of all n factorial permutations of 1 up to n. If we number the corners of an n-gon, every symmetry canonically defines a permutation. However, not every permutation of the corners necessarily is a symmetry, unless n equals 3. Indeed, every permutation of the numbers 1, 2, and 3 can be realized as an element of D3. For example, we can permute the corners of a triangle however we want, with either a rotation or a reflection. For n equals 4, we can see right away that we lose this property. So 1, 2, 3, 4. There is no way that we'll swap 1 and 2 without also swapping 3 and 4. It follows that the groups Dn and Sn are isomorphic for n equals 3 and non-isomorphic if n is bigger than 3, because Sn is strictly bigger than Dn in that case. Instead of using configurations of the triangle, let's now consider rearrangements of the numbers 1, 2, and 3. So we can write these as words, and there's 6 of them. Clearly, S3 canonically rearranges these configurations. But when I say canonical, there are two perfectly acceptable interpretations for what that means. And I touched upon this near the end of the last lecture. For example, 1, 2 can be interpreted to mean swap the numbers in the first and second coordinates, no matter what they are. Alternatively, 1, 2 could mean swap the numbers 1 and 2 regardless of where they are. I touched upon this a little bit in the previous lecture. Recall that I had a picture just like this. And please watch that lecture if you have not. But there, instead of representing permutations as words like this, I wrote them as vectors. In this picture, I wrote them as column vectors, x1, x2, x3, for example. And this one over here as row vectors, so x1, x2, x3. And then applying the permutation, either 1, 2, or 2, 3, as we travel around the edges, corresponds to multiplying by the corresponding permutation matrix, either on the left if we have column vectors, and on the right if we have row vectors. And recall in that setting, there's this duality to that. So with the row vectors, well, let me start with the column vectors first. The x1, x2, x3 got mapped to x pi 1, x pi 2, x pi 3, whereas the column vector x1, x2, x3 got mapped to x pi inverse of 1, x pi inverse of 2, x pi inverse of 3. Now when we get to chapter 5, we'll understand this in the context of group actions, and this being a left versus right group action. And there is this duality. Every left action is a right action by the inverse element. But here, when we just look at what we're doing, swapping numbers versus swapping coordinates, it kind of hides this duality. So over here, let's take 2, 1, 3, and let's swap the numbers 2 and 3. If we do that, then 2 and 3 swaps places, and we get 3, 1, 2. But over here, if we swap the numbers that are in coordinates 2 and 3, that will swap 1 and 3, and we get a different configuration, 2, 3, 1. So I like this setting here. I think it's a little bit less confusing, swapping numbers versus swapping coordinates. But it kind of hides the fact that there is this underlying duality between a permutation and its inverse behind the scenes. Okay, let me give a name to a type of permutation that I've been using and I will continue to use a lot, and that is a transposition. That's any permutation that swaps two objects and fixes the rest. So something like ij. Here it is in cycle notation, and here it is in the permutation diagram. An adjacent transposition is one of the form I plus 1. The following fact should be intuitive if one thinks about rearranging n objects in a row, and that there are three canonical types of generating sets for Sn. And when I say intuitive, I mean the fact that these are all generating sets should be intuitive. The word canonical is, maybe it's overused. It just means natural, and it's not a formal concept. So what's I call canonical or what's natural to me might not be to everybody. But I think you will agree once we get through these that these are all very natural generating sets. So first of all, a transposition and an n cycle. So let me draw a picture with this. Suppose you have a circular table, 1, 2, 3, 4, 5, 6, and you are allowed to swap. So these are seating like chairs or positions, and you are allowed to have two people who are in the first two chairs swap positions, no matter who they are. And you're also allowed to cyclically shift the seating arrangement, so everyone can get up and rotate by one chair. Hopefully it's intuitive for you to see why I can create any seating arrangement, any permutation of say, people in these chairs with these operations. So that the chairs aren't moving, but the people, maybe Alice, Bob, and Charlie, etc., are moving. Now, I should say that not every transposition and every n cycle will work. So, for example, if I try to do 1, 3, and then 1, 2, 3, 4, 5, 6, I claim that I am not going to get S6. So what I have above is that if I have, what I claim is if I do 1, 2, and then 1, 2, 3, 4, 5, 6, that I will get all permutations. And hopefully you can see that. But it's a little subtle because I claim that this is not going to be S6. And to think about, see why this is, imagine that the seating arrangements are alternating gender. So this is boy, girl, boy, girl, boy, girl. And if I allow the transposition of 1, 3, then I'm going to swap two boys or two girls, depending on where they're sitting. And then this is a cyclic shift. So this is not going to change the relative boy, girl order, nor is this. So it's not entirely obvious that this will generate S6. It's more of but hopefully it's intuitive, and it's more of the formal proof of it is more of an exercise in notation, and that's something that I relegate to exercises in my book. So that's one way to generate Sn. That's probably the most common. Another way is with adjacent transpositions. So for this one, imagine that you have n people sitting in a chair. So I'll do 6 again. 1, 2, 3, or n people sitting in chairs. 1, 2, 3, 4, 5, 6, and you are allowed to swap the people in the first two chairs can swap places. The people in the second and the third chair can swap places. The people in the fourth and the fifth chair can swap places, and the people and so forth, or the third and fourth. And then I'm running out of color, so let me just do this. I don't think it's hard to see that if you're allowed to swap with your neighbor, you can get any permutation of people sitting in these chairs. And finally, this last one, overlapping transpositions. This is similar, but here we have 1, 2, 3, 4, 5, 6. So now everyone is allowed to swap into the first chair as needed. So 1 and 2 are allowed to swap. 1 and 3 are allowed to swap. 1 and 4 are allowed to swap. And I don't know if I want to do this entirely. 1 and 5, and then sure, I'm almost done. 1 and 6. So maybe it's a little bit trickier to see that this works, but convince yourself that this does as well. these are not the only generating sets, and maybe these are, maybe a better way to say this is that there are three canonical types of minimal generating sets, because for all of these, if you remove anything from it, it no longer generates. Clearly, if you remove the n cycle or the transposition, you cannot generate Sn. If you remove one of these, it's like you are breaking. If you remove, say, 3, 4, then it's almost like you're chopping this right here, and people on the left side cannot move over to the right-hand side. And there's a similar argument that you can make here. This was a worthwhile example to do because it shows how you can have a group, let's say S100, that is generated minimally by two elements, say 1, 2, and 1, 2, the n cycle 1 up to 100. But it's also generated minimally by 99 elements. So 1, 2, all the way up to 99, 100 transpositions. So in a vector space, every minimal generating set, every basis has the same size, every minimal generating set has the same size. That's the dimension. But in a group, here's a group generated minimally by two elements or by 99. Okay, let's move on. I'm going to show you some fun pictures of Cayley graphs of symmetric groups, but first I need to talk about polytopes. A polytope is a finite region of n-dimensional space enclosed by finitely many hyperplanes. What do I mean by that? Let me show you some examples. So, two-dimensional polytopes are polygons. Now, what does that have to do with hyperplanes? Well, let me draw a square. And if we're in R2, then a hyperplane in general is just a line or a k-dimensional plane that's one dimension lower than the space. So in R2, that's a line. And this square region we can describe as being enclosed by the following four lines. I could write this formally with inequalities and say it's like the things above this line, below this line, to the left of this and the right of that. But I think just this picture, you can see what I mean by enclosed by finitely many hyperplanes. And other polygons, they don't have to be regular, any sort of convex, convex polygons can be defined like this. And then the three-dimensional version of this are called polyhedra, things like cubes and tetrahedrons and dodecahedrons. But again, those are the regular ones. What do I mean by regular? Well, the formal definition of a regular polytope involves the technical condition of its symmetry group that I will not give you. But informally, it means that all faces and all vertices are identical and indistinguishable. These are higher dimensional analogs of regular polygons. There are exactly 5 regular polyhedra, that is three-dimensional polytopes, and these are called the Platonic solids. You've probably seen these. There's the tetrahedron, or the triangular pyramid. There's the cube, the octahedron, which is its dual, the dodecahedron, and its dual, the icosahedron. And by the way, what I mean by dual doesn't really come up in this class very much, but let me just tell you is if you swap the notion of vertices for faces of a polytope, then you get its dual. So if you take a cube and you put, I don't know how I can draw this, well, but if you put a dot in the middle of each face, so that's the bottom face, this is the back face, this is the left back face, then what you have is and you connect these all up. Sorry, I'm not drawing this all that well, but you get the idea. You get this is the octahedron. And similarly, if you do this, it's the same thing. Here you put a node in the middle of every face. Now there's 2 in the back. There's like one there and one there. Again, I'm not sure how well to draw this. Well, then you get a cube. So these are duals of each other. These two things I'm definitely not going to try to draw that, are duals of each other. And then the tetrahedron is self-dual. It is its own dual. More general than the Platonic solids are the Archimedean solids. These are non-regular convex uniform polyhedra, but they're built from regular polygons. Though they can involve different polygons, so one might involve a square and a triangle, for example, all vertices are locally identical. So if you're at one vertex, it looks the same as every other vertex. In the 3rd century BCE, Archimedes, for whom these are named, classified all such polyhedra, and there's 13 of them. 5 are truncated versions of the Platonic solids formed by chopping off vertices, and the others consist of the chiral snub cube and snub dodecahedron. I'll show you pictures of these soon. And by chiral, I mean it is not equal to its mirror image. So it's like the 3-dimensional version of a pinwheel. There are hybrids, such as the icosahedron, and then there are truncated versions of these hybrids. And you can ask, why not just keep going and chopping things off and taking hybrids, and maybe there's infinitely many of them. But Archimedes showed that there was just 13 of them, and I think that's a pretty remarkable achievement for, given what time frame that was done in and what tools and what knowledge he had to work with. The Cayley graph of S4, and actually a few other related groups, can be arranged on the skeletons of several of these Archimedean solids. These are the 13 Archimedean solids. Here are the 2 chiral ones. They are not equal to their mirror images, the snub cube and snub dodecahedron. Here are the 5 truncated versions of the Platonic solids. And then there are these 2 hybrids, cuboctahedron and icosahedron. And then these other 4, I think these are truncated versions of these 2. I'm not sure the difference between small and great. I brought up this word on Wikipedia, rhombic icosahedron, and it says that's short for truncated icosahedral rhombus. I'm not sure exactly what that is, but I think this is a truncated version of that just by looking at the picture. And I think there might be several ways to truncate things to get others, and maybe that's why they're small and great, but that Wikipedia page didn't have great on there at all. So it's fun to do a deep dive with like a Google image search or Wikipedia on these Archimedean solids and all the links within them and other pictures and their duals. So I don't know too much about this. It's not really the point of this lecture, other than just to show you some pretty pictures, and some of these will come up later when we look at Cayley graphs. Here is our first example of an Archimedean solid. I'm going to define it a little bit differently, geometrically. So the n-permutahedron is the convex hull of the n factorial permutations of the vector 1, 2, all the way up to n in n-dimensional space. This is an n-1 dimensional polytope because this vector and all permutations of it lie on the hyperplane x1 up to xn equals n-1 times n over 2. This is just the sum of the numbers from 1 up to n, which is satisfied by all n factorial of these vectors. I'm going to try to draw a picture of the 3 permutahedron. So what I'm drawing now is not the unit cube in R3, but it's going to be the cube of side length 3 in R3. So we have the x-axis here, we have the y-axis here, and we have the z-axis here, and each of these will have length 3. So I've never actually done this before. So 1, 2, 3, and 1, 3, 2. Let me try these. And so 1, 2, and then you go up to 3, and maybe, so that might be something, maybe this point. So this is 1, 2, 3. 1, 3, 2, so that's 1, 3, and then you go up to 2, so maybe that's here. 1, 3, 2. Let me pick a different color. for 2, 1, 3. So for here I go 2, I go 1, then I go 3. That's going to be somewhere like there. So this is 2, 1, 3. Let me try 2, 3, 1, 2, 3, 1. That's going to be down here. That's 2, 3, 1. And then let me do 3, 1, 2. So if I go 3, 1, 2, that's going to be 3, 1, 2. And then 3, 2, 1. That's 3, 2, 1. That's going to be down here. 3, 2, 1. So the convex hull is, well, the convex hull, if you're in the plane of a bunch of points, is what you get by taking like a rubber band and stretching them around these, and it's everything that's inside of this. You can imagine a three-dimensional version of this if you have a bunch of points in three-dimensional space. Imagine you take like, visualize this in 3D however you want to. Imagine you take saran or like plastic wrap and you stretch it around this, you're going to get some polytopal structure. That's the convex hull. So in here, the convex hull is just going to be, let's see, what color do I want to use? Well, let's use gray. So it's going to be, I don't know. No, I'll use black. It'll come out better. So it's not approved, but it seems reasonable that it's going to be this hexagon right here. And think about how these edges are related. So these vectors differ by swapping, what is it? The coordinates 2 and 3, or the numbers 2 and 3, same thing. Let me actually make that blue. These two things differ by swapping, let's see, 1 and 2, the numbers, not the coordinates. So let's be consistent with our previous pictures. Let me draw that green. Here I'm going to guess swapping the numbers 2 and 3. So yeah, 2 and 3. So this is, and then here we're going to swap the numbers, I assume 1 and 2. Yep, positions 2 and 3. So we've seen this before. Here we swap the numbers 1 and 2. Wait, sorry, 2 and 3. So they're in the first and the third coordinate. And here we swap the numbers 1 and 2. So yeah, does it look familiar from this lecture and the previous one? The 3-permutahedron is a hexagon. It sits in this this plane that goes kind of this way of, I'm not going to try to draw this, but x1 plus x2 plus x3 equals 6, because the sum of each of these entries is equal to 6. So this is one where, so I call this is swap numbers. And I think we said that this was a left Cayley graph. Or in other words, and it's not written here, but I'm going to say that I'm going to call this the left n-permutahedron. And you can imagine how the right permutahedron is going to be defined as well. You can take these points, the same points, and you can just connect two things that differ by swapping coordinates instead of digits. I'll let you draw this. I think I'm just going to it'll be a disaster if I try to draw it on top of that. What I do want you to notice is that if you take any two of these points and compute the length of this edge, that you are going to get the square root of 2. Because, what's this length? It's 2 minus 1 squared plus 1 minus 2 squared plus 0 squared. So that's root 2, and all of these are going to be root 2. If you do the other definition and you connect things with adjacent the coordinates differ by swap instead of this, you're going to get lengths, I think, of root 2, root 8. You're going to get 3 different lengths. So it's not going to be a regular hexagon like this is. More generally, the n-permutahedron is the Cayley graph of Sn generated by adjacent transpositions. Here's an example for S4, generated by 3 transpositions. Now, both of these live in 4-dimensional space, but they are three-dimensional polytopes because x1 plus x2 plus x3 plus x4 is equal to 1 plus 2 plus 3 plus 4, which is 10. And I should say that over here, all of the edges have length root 2. So this is maybe a little bit more indicative as to what this thing actually looks like in four-dimensional, I guess, in this three-dimensional space. Whereas over here, if you look at like this edge down here and compute its length, well, it's the square root of 4 minus 1, so 3 squared, just by the Pythagorean theorem, 3 squared plus 3 squared plus 0 squared plus 0 squared, which is root 18. Whereas what's a different one? Up here, they differ. So this green edge, it's length 1 squared plus 1 squared plus 0 squared plus 0 squared, which is root 2. So this is the combinatorial type. I should say it's not obvious that they have the same combinatorial type, that these are both truncated, what are they, truncated octahedrons, I think. But I guess one way to see it is that this is a, which one is it? This is a right Cayley graph, and this is a left Cayley graph, as we saw earlier in this lecture and also in the previous lecture. So if you pick a home state in these, let's call this one the identity, and this one the identity, and then you label all of the nodes by elements in the group, then if you replace each pi with pi inverse, that will take one of these permutahedron to the other one. Again, that's not a proof because we haven't developed a theory and formalized this stuff, but hopefully it's intuitive as to why these things really should be isomorphic. We just saw the n-permutahedra, which are truncated octahedra, but also Cayley graphs generated by adjacent transpositions. So let's dig into this a little bit further. Even though every permutation in Sn can be written as a product of transpositions, there are many ways to do this because there's many paths in a Cayley graph. For example, 1, 3, 2 is 1, 2, 2, 3. Remember, we are reading from left to right. But I can just multiply by 2 extra copies of 2, 3. That doesn't do anything. Or by 2 more copies of 1, 2. However, the parity, that is whether it's even or odd, of the number of transpositions of a fixed permutation is unique. So 1, 3, 2, there's many ways to write this. Like with 2 transpositions or with 4, we can do it with 6, but we can never do it with 3. I will not prove this here. It can be proved using elementary methods. It's a bit notationally messy, and I don't think all that insightful. I think I do in the back of my chapter 2 exercises in my book have an outline of it. But if we wait till chapter 4, when we learn about the isomorphism theorems, there will be like a one-line proof. And so there's no harm in waiting because I'm not going to use this result to prove other things. I'm just going to use it to illustrate some examples. What it means is that there is a well-defined notion of an even permutation in Sn, which is one that can be written with an even number of transpositions, like this one up here, and an odd permutation, which requires an odd number. So every permutation is either even or odd. It is elementary to see that the product of 2 even permutations is even, 2 odd permutations is even, and an even and an odd permutation is odd. When I say elementary, why is this? Let me just do an example that hopefully you'll see why if you don't already. Suppose you have 2 permutations, and let's say pi is like odd. So it's like AB times CD times EF. These don't necessarily have to be distinct, these letters that I'm writing. And let's say that sigma is like GH times IJ, so it's even. So what we have is we have an odd number of permutations here, and we have an even number of permutations here. We concatenate them. The parity of the number of these is just odd plus even, which is odd. So that's where this one comes from, and it's easy to see how to generalize this and modify it for these other 2 cases. The set of even permutations in the symmetric group Sn is called the alternating group, and it's denoted An. Not surprisingly, exactly half of the permutations in Sn are even, which means that the size of the alternating group is n factorial over 2. I say not surprisingly because that's what you kind of expect holistically, that half are even and half are odd. It's not obvious. And there is an element, there's probably several elementary proofs. I think I actually outlined 2 of them in my chapter 2 exercises in my book. But again, I will not do them here because it also follows quite easily once we know the isomorphism theorems in chapter 4. And we're not going to use this to prove other things. We'll just use this as an example. Here are Cayley graphs for A4 on 2 Archimedean solids. Here is the truncated tetrahedron, and on the right is the cuboctahedron. So this layout actually is something that was inspired by Nathan Carter's visual group theory book. I'm using A, B, C, and D to represent the 3 cycles. Here I think A can be taken to be any 3 cycle. I might as well just take 1, 2, 3. And X can be taken to be any, that's this edge, any product of 2 cycles. I think X being 1, 2, 3, 4 will work. And then I'll leave it as an exercise for you to label these things. I think A squared is this squared, so 1, 3, 2. The reason why you don't have X squareds and Y squared is because these things have order 2. Now in my lecture 0, highlights of visual algebra, and we'll see this in chapter 3 again, I gave an example of this Cayley graph that was like a flattened version of it. Let me just sketch what that looks like. So if you have a central triangle like this, and then you have 3 triangles and they're all oriented in the same direction. And then you have these blue arrows that connect out here. You can make it flatten kind of like this. Now over here, if you pick one of these nodes and you call it the identity, you can pick your favorite color. Let's, I don't know, say purple. And let's say that purple is I don't have a name for it, is 1, 2, 3. And then you might think that A4 is generated by this, and then any other 3 cycle. But you have to be careful. So let's try 1, 2, 3. Let's try 2, 3, 4. So what's 1, 2, 3 times 2, 3, 4? 1 goes to 2, 2 goes to 3, so that's 1 goes to 3. 3 goes to 1, 1 is fixed, so that means 3 goes to 1. So 2 goes to 3, 3 goes to 4, 2 goes to 4, hopefully 4 goes back to 2, 4 is fixed, 4 goes back to 2, exactly. So this here is order 2, but if you do 1, 2, 3 times 2, 4, 3, for example, let's see what that is. You would think, oh, maybe you get the same thing. But 1 goes to 2, 2 goes to 4, 1 goes to 4. 4 is fixed, 4 goes to 3, 4 goes to 3. 3 goes to 1, 1 is fixed, so we get that. And hopefully 2 goes to 2, 2 goes to 3, 3 goes to 2, 1, 4, 3. So this has order 2, this is order 3. So what happens when we do the purple-green path? So we do the purple-green path, we get purple-green, purple-green, we get something of order 2. So if this is the identity, then this, so if this is 1, 2, 3, then this has to be 2, 3, 4. It is not going to work at all if we do 2, 4, 3, because that would be something that would have, this has order 3, and this purple-green path has order 2. So you have to be careful when labeling these nodes. You have a lot of degrees of freedom, but you don't have complete degrees of freedom. So let's write this down: 1, 2, 3, and 2, 3, 4. And I will say from experience, and I assign this as homework and then I take tons of questions, it's really insightful to take these blank diagrams and fill them out with permutations. It's a great way to practice cycle notation as well. Many books will just have a list of like compute these products of permutations, and just a list of randomly generated ones, but it's much more informative, I think, to do it here because you get a lot more practice. And then you get this finalized diagram, and you see a lot of patterns as well. So like, where are the 3 cycles located? Where are the products of 2 cycles? How are they distributed among here? And then that's helpful for when we'll go study cosets in the next chapter. Let's return to something we've seen before. This is the permutahedron, a truncated octahedron, and a Cayley graph of S4, where the generators are adjacent transpositions. I've declared this node to be the identity, and now I've colored in yellow all of the even permutations. These are the nodes that are of an even distance from here. So this node is a distance 2 from here, but you can also get there with a distance 1, 2, 3, 4, or a distance 1, 2, 3, 4, 5, 6, but never 5 or never 7. So obviously there cannot be 2 adjacent nodes that have that are both even transpositions, so there's no adjacent yellow nodes. And you can see how these are distributed. It's not surprising that this antipodal node is the furthest one away, so this is the only permutation that requires 1, 2, 3, 4, 5, 6. This is a product of 6 transpositions, and if you label these with configurations, well then this is 1, 2, 3, 4, and this is 4, 3, 2, 1. It's the most scrambled configuration of your home state. Over here on the right is the Cayley graph of S4 with a different generating set. This was one of those 3 canonical ones that I said in the beginning, where all the transpositions have a fixed number in them, in this case 1. This is on a graph, not a polytope, but it's called the Nauru graph, and the name of it comes from the fact that there's this 12-pointed star here, and Nauru, I don't know, maybe a few of you have heard of it, is a tiny island country in the middle of the Pacific Ocean, just below the equator. I think it's got like 12,000 people who live there, and it's like 8 square miles. So it really is tiny. And yeah, that just this 12-pointed star inspired the name of this graph by graph theorists to be called the Nauru graph. So once again, notice the even permutations are in yellow, and it's not a proof that the odd permutation, that there's the same number of even and odd permutations, or that definition is well defined, but hopefully it's intuition for why it is true. Mostly because it's fun, but also because it's insightful, I want to show you 2 more examples of Cayley graphs for S4 that sit on the skeleton of an Archimedean solid. I also want to show you how A4 appears in these as a subset. So for this, I need the notion of cycle type, and I will define this formally later, but I think it should be clear from this example, from the context, what I mean by it. So if I say that there are only 5 cycle types in S4, and let me just say that there's one identity element, which is an even permutation. There are 6 transpositions. These are 2 cycles. Those are odd. There are 8 3 cycles, which are even. They're products of 2 transpositions. There are 6 4 cycles that are odd, products of 3 transpositions. And then there are 3 products of 2 cycles. Those are even. You can just see them right here. So by cycle types, I mean the number of cycles of each length. So here you have identity element, you have a 2 cycle, a 3 cycle, a 4 cycle, and a product of 2 cycles. And you can see how this will generalize for a larger n. At left is a Cayley graph for S4 built on a truncated cube, and at right is one built on a rhombocubooctahedron. So let me say a few words about this. So going over here, this red arrow has to be a 3 cycle. So I say 2, 3, 4 here. Let me pick. Yeah, let's do that. 2, 3, 4. I almost did 1, 2, 3. And then this thing will be 2, 4, 3. And then what does this purple thing have to be? So it's tempting to say, well, it's got to be something of order 2. And so this has order 2, a 2 cycle, but also these have order 2. But I claim that this is going to have to be an odd permutation. And here's why. Because if we try to put an even permutation right here, then both generators will be even, and we won't generate all of S4. So this has to be odd. So let's let it be a transposition. Let's say 1, 2. Now, I don't have total choice. I can pick any 3-cycle here, but I can't pick any transposition here, because if I pick something that doesn't contain a 1 in it, like if I pick 2, 3 or 2, 4 or 3, 4, then neither of these permutations will move 1, and I will not generate all of S4, because I will only generate permutations that move 2, 3, and 4, which is S3. So once I pick this to be 2, 3, 4, this thing has to be either 1, 2, 1, 3, or 1, 4, and then I can go finish the rest of the diagram. Now notice that because a 3-cycle is even, then anything connected by red arrows are either, all of these little triangles are either all even or all odd. So these are all even. You apply an odd permutation, and now these have to be odd. When you apply another odd, now you get an even permutation, so these are even, and so forth. So you can see the even permutations here. Just for fun, I will say that there's a variant of this Cayley graph where, so notice here that all 8 of these triangles are in the counterclockwise direction. You can build a Cayley graph where every other one is in the opposite direction. So where this is counterclockwise, this is clockwise, clockwise, counterclockwise, etc. And you actually, in this case, if you do that, you won't get a Cayley graph for S4. I think you'll actually get one for A4 cross S2, which also has 24. That group will have an element of order 6. You can check here that the order of these elements, let me write them up here because I don't have it in this table. The order of these elements, 1, 2, 3, 4, and 2. So now going over here, once again, this is has to be a 3-cycle. So we can just pick a 3-cycle. Let's do 2, 3, 4 to be consistent with what we did before. And now this blue thing has to be a 4-cycle, so we can really pick, I think any of these will work. I'm pretty sure, I'm not 100%. So if we do, say, 1, 2, 3, 4, we should be able to fill out the rest of this diagram, again, by just by composing permutations, and it's good practice to do so. It's possible that we might run into issues like what we did with A4 in the previous slide, where we couldn't pick 2, 3, 4 or 2, 4, 3 at will. We had to pick one of them, but I'm pretty sure that both of these, that once you pick a 3-cycle here, any 4-cycle will work. But don't hold me to that. It's worth checking, and let me know in the comments if that's not right. Once again, the red arrows are 3-cycles, so the even permutations are clustered like this. It is worth seeing the cycle graph of S4. Remember, these cycles here are maximal orbits. This looks like a drone or a UFO. So there's 6 transpositions that generate 2 cycles. Each 3-cycle generates a orbit of size 3, and then each 4-cycle generates an orbit of size 4. And the square of the 4 cycles are the products of 2 cycles. It's worth noting that the subgroup A4 consists of these 11 elements and the identity. We've seen a few Cayley graphs of the alternating group A4, so let's see a couple for A5. Here's the first one. A5 is a very important group, and it has special properties that we will learn about later. So we all know from high school that there's a quadratic equation to solve any degree 2 polynomial. There is also a cubic and quartic one, though they are much more complicated, but there is none for degree 5 polynomials. There are such polynomials that cannot be solvable with radicals, and that has to do with special properties of this group A5. I'm not making this up. That's what was discovered by Galois in the early 1800s, when he was like 20 years old, and really gave birth to the field of group theory. So here's the Cayley graph generated by the 5-cycle, 1, 2, 3, 4, 5, and the product of transpositions 1, 2, 3, 4 on a truncated icosahedron. It took me a very long time, several hours, to make the Cayley graph on the previous slide. So I want to show you examples that I did not make of other Cayley graphs of symmetric and alternating groups on Archimedean solids. So these all come from the website WED's List, made by Nick Wed, who is a retired biotechnology professional in the UK. He's also a bit of a math hobbyist, and he has, if you go to wedslist.com, he's got a blog of a bunch of things, including math, especially math involving visuals. And he has one page, namely this one here, that has a list of all the Archimedean solids and Cayley graphs that can be built on them. And also I think there's one or two where there are none, and some of them have multiple examples. And then there's also things that look like Cayley graphs that are not. So here, I think the first three of these are all A5. I'm not going to write down what they are. I'll just tell you. This is a truncated dodecahedron. This is a snub dodecahedron. That's one of the chiral ones. And this is a small rhomba icosahedron. I think I said that right. Then this is S4. What do I want to put? This is S4. This is S4 cross C2. So it's not a symmetric group, but it's direct product of 1 with C2. And this is A5 cross C2. This is a snub cube. This is a truncated cuboctahedron. And this is a great rhomba icosahedron. So I encourage you to check out this website. You never know, it may be offline one of these days, but there's always the Wayback Machine. You can always plug this in and figure out and look at an archived copy. So hopefully this will live on forever. There's a lot of really cool stuff on this website. I encourage you to check it out. I want to finish this lecture with a comment about symmetry groups of Platonic solids. So the two-dimensional regular polytopes are just n-gons, and we have seen their symmetry groups. They are dn. But if we are not allowed to reflect, like if we are living in flat land and we are not allowed to pick up and flip over the n-gon, then the symmetry group is just Cn. We say that this is the rotational symmetry group and this is the full symmetry group. And this is the two-dimensional case. The Platonic solids are three-dimensional regular polytopes. They also have symmetry groups, and we can speak of their rotational symmetry group as well as their full symmetry group, depending on whether or not we want to allow a reflection. Now, allowing a reflection, let's suppose we have a cube, and we label the nodes, say 1, 2, 3, 4, 5, 6, 7, 8, like we did in the first chapter. Now, there's nothing wrong with, it's natural to allow a reflection about like this, I don't know how to draw this well, this central plane, because that's just going to swap these labels. But if we're holding this cube in front of us, we can twist it and rotate it, but we can't perform this reflection unless we like go into four-dimensional space. Just like how we can't, take a reflection of a triangle in sitting on a table in front of us unless we pick it up and go into two-dimensional space and then flip it over and put it back down again. So basically, these are different types of symmetry groups, and I think it's really interesting that the rotational symmetry groups for these are all either A4 or S4. And then the full symmetry groups, these are either S4 and then S4 or A5, direct product of that with C2. And we saw Cayley graphs for all of these. We have seen them so far. I guess we saw this one and these on the previous slide. And I guess I didn't show you S4 cross C2, or did I? I don't think I did. But I explained to you a couple slides ago how to construct that from a Cayley graph from S4. Remember, if we take if we reverse the orientation on half of those triangles on the truncated cube, we get the Cayley graph for S4 cross C2. So that's the story in 3 dimensions. So what about in higher dimensions? Well, the icosahedron and dodecahedron are only in 3D. They don't exist in higher dimensions, so those are out. But the tetrahedron, or sometimes called the n-simplex, this exists in all dimensions, as does the n-dimensional hypercube, and its dual, which is sometimes called the cross polytope. The octahedron is just the special case of it in 3 dimensions. Now, in four dimensions, you get something called the 24 cell, which is self-dual. You get something called the 120 cell, and its dual is the 600 cell. These are all 4-dimensional polytopes. And the symmetry groups of these are Weil groups or Coxeter groups. I don't know how to describe them other than just say, just Google it. And these exist only in 4D. Once you go beyond that, these are the only higher dimensional polytopes that you get. So in some sense, it's kind of boring. The symmetry group of the tetrahedron in any number of dimensions is Sn. So just like the triangle and the tetrahedron, you can achieve any permutations of the corner that you want. And then the symmetry group of the n-dimensional cube and its dual is something we haven't seen yet. It's a wreath product of Sn with C2, sometimes called the signed permutations. So if one way to describe this is if the symmetric group is a way to shuffle a deck of cards, playing cards, then the wreath product is a way to shuffle the deck of cards where you are also allowed to flip them upside down. So that's a good place to stop. But I do want to say that thus far in chapter 2, we have seen cyclic, abelian, dihedral, and permutation groups, especially the symmetric and alternating groups. These are classic examples that will come up in any intro group theory course. But what's coming up next really is not. So we'll see the quaternion groups, but we'll see dicyclic groups, generalized quaternion, diquaternion, semidihedral, and semi-abelian groups. And these are pretty exotic. Because they're typically unmotivated by their presentations, but they really come to life when you see the Cayley graphs. You can see their similarities and differences. And as we start to explore them in the coming lectures, but also in later chapters, we see that they really embody well key features of groups, like cosets and normal subgroups and quotients that we haven't learned yet, but we will in the future. And as such, they will be key examples to have in our arsenal going forward. In the immediate next lecture, we'll start with the familiar quaternion group and see how to generalize that to get the dicyclic groups. And then we'll do a trick that I like to call dihedralizing the quaternions. That's the name of an article that I just published in the American Mathematical Monthly to create a new class of groups called the diquaternion groups. And I've never seen this family of groups named really anywhere. So that's brand new. It's a lot of fun. I think you're really going to like it. So stick around.